Hello everyone, welcome to Algebra 1 with Miss Betsy. We're going to be continuing our study of word problems today, and we're going to be talking about motion problems. And these are a very common real-life actual application of algebra that you can use. We're going to be continuing with our text, which is the second edition of Algebra 1 as it's published by Bob Jones University Press. Again, it does not track completely with the third edition, but you can still gain valuable information from this video. Let's go ahead and pray, see what our lame joke is for the day, and then we'll dive right into our material. Father God, I thank you for another day of life that you've given to us. I thank you that you know us and that you are alive and at work in our lives. God, I ask that you would give us ears to hear you today, to follow hard after you, and Father, I ask for the focus and the concentration necessary both to learn this material and for me to be able to communicate it to them. Help us to honor and glorify you in all we do, and I pray in the name of your Son, Jesus. Amen. Okay, here's our joke for today. The rooster flies up to the top of his chicken coop and he lays an egg. And I'd like to know, is that egg going to roll to the north side of the chicken coop, or is it going to roll to the south side of the chicken coop? Now, this is where we tell the city folk from the country folk, roosters are not the ones that lay eggs. Hens are the ones that lay eggs. So he can fly up to the top of his chicken coop and try all day long, but he is not going to lay an egg. So, Section 4.9, Motion Problems, is found on page 163. And here's a story. A jet leaves O'Hare Airport in Chicago at 7 a.m. and flies south towards Atlanta, 606 air miles away, at an average rate of 420 miles an hour. An hour later, a jet leaves Atlanta and flies towards Chicago at an average rate of 500 miles an hour. Because of an error in calculations, the jets are flying at the same altitude and on the same route toward each other. How much time do the air traffic controllers have to change the direction or altitude of the jets before they collide? In other words, when are they going to run right into each other? And this is a classic rate problem that you're going to learn how to solve today. Now, of course, our word problems that we do, they're assuming everything's constant, and there's lots and lots of variables in real life that you have to consider when you're finding an actual answer like this, but the principles are exactly the same. So this problem that we just read is called a motion problem, and you have been working with motion problems for a long time. There's a very simple formula that you use, and it's D is equal to R times T, where we have distance for D, we have rate for R, and we have time for T. And this is an application that you've used forever, okay? If you have been driving 3 hours and you've been going 50 miles an hour, how far have you driven? You've driven 150 miles. If you drive 200 miles and you drive at a rate of 50 miles an hour, how long have you driven? Well, you've driven 4 hours. Here is our first problem. Distance is equal to our rate, which was 50 miles an hour, times our time, which was 3 hours. How far have we driven? 150 miles. That's very basic, very straightforward, very easy. And then I said, okay, we have driven 200 miles. We went at a rate of 50 miles an hour. How long did we travel? And they will very, very frequently, very commonly use T for time in distance problems. How do you solve this? Well, I told you it was 4 hours because you automatically know what you've done. But to solve this equation algebraically, to isolate t, we're going to divide both sides of that equation by 50, and that's how you arrive at the answer here, that you had traveled for 4 hours. And then let's say that you traveled 150 miles, and you traveled for 5 hours. How fast were you traveling? Well, your rate is how fast you were traveling. How are we going to solve this equation? This is simple, isn't it? You know that you were traveling 30 miles an hour because when you divide both sides of that equation by 5, you end up with R being equal to 30 miles an hour. And these are just 3 examples here of how we use the distance formula, which tells us distance is equal to rate times time, to solve. And we can either find the distance we've traveled, the time we were traveling, or the rate at which we traveled. We're going to be using this anytime we work with a distance problem, and we're going to actually see that it's going to be very, very beneficial to us to use a chart and have a chart filled in. It'll be similar to the charts that we used for our last unit, which was on coins, but it'll be smaller because we only have 3 columns. We have distance. Actually, we're going to go rate times time is equal to distance. And this is our little chart that we're going to fill in. Rate times time is equal to distance. And they give you almost a meaningless illustration on page 164. Here's example 1. It says, Jim rides his bicycle at a rate of 8 miles an hour for t hours. How far does he ride? Well, let's pick a variable. We're going to say, let D equal the distance Jim rides. Now we want to put in the information that is given to us. How fast is he riding? He's riding 8 miles an hour. And how long does he ride? It says he rides t hours. So distance right here, which is what we're finding, distance is equal to what? Rate times time. So here, all we have to do is fill out this chart and we have our answer, that the distance Jim rides is equal to 8 times t. If he rides for 2 hours, he rides 16 miles. If he rides for half an hour, he rides 4 miles. So this is what we're going to do to solve distance problems, but the work is going to be significantly more involved. So let's go ahead and look at example 2 now. And this one, I don't believe I just erased that. This one is a good bit more involved. So let's just hang in there with me and you'll see that it all makes sense. We have rate times time is equal to distance. This is going to be our chart that we set up. Let's read the problem and see what we have. The junior and senior high Sunday school classes are going on a hike. The junior high class leaves the church and travels east at 3 miles per hour. The high school class leaves an hour later, traveling at 5 miles per hour on the same course. How much time will pass before the senior high class catches up with the junior high class? So we want to look at this and we want to read it really, really, really carefully. when we want to figure out what is the main question that they're asking, or what is the main unknown. And right here in this problem, they want to know the time that passes before the senior high school class catches up. That's right in the very last sentence. It says, how much time will pass before the senior high class catches up? And what that actually is how long does the senior high class travel? Because junior high class leaves first. So they're going to catch up, and it's going to take the high school class the entire time to catch up. So we're going to say let x equal the time the senior high class hikes. That's what our variable is going to be. And now they say to draw a picture that describes the problem. And I think on a lot of these distance problems, you have to draw a picture. Maybe you can see everything in your head, but I even see things much more easily at times with distance problems. It helps you understand what's going on. So what is it that we want to find? Here's the church, and let's just say we're meeting them at the park. What do we want to figure out? We want to figure out how long it is, how long the time is that the senior high class hikes. So they're going to start here, and this is going to be the time the seniors hike. Obviously, that's the whole time. Now, how long is it that the junior class hiked? Well, they started at the same place, and they ended at the same place. Okay, so the distance is the same, but the time, I'm going to do this sketch here a little bit differently than they show in the book. Because we're talking about, distance is the same, so they cover the same amount of actual mileage. But if we have this line be our time, isn't it true that the junior high class traveled a longer amount of time? And I'm sorry, I have allergies. Excuse me. And no remote for this video. But the junior high class traveled an hour longer. So they traveled the same amount of time that the senior high class traveled, which is x, and they traveled an additional hour. So this time here, before the senior high class started, the junior high class had been walking for a whole hour. And that's an important piece of information. Now, we read, we plan, we solve, and we check. Those are the 4 steps that are involved in solving word problems. So the second one is plan your strategy. We want to set up our table that we can use to see what our rate times time equals distance. We're going to see how that helps us. So let's have rate times time is equal to distance. And we have the junior class. And we have the senior class. Except I want to use a different color. We have the senior class. How long did we say the senior class traveled? This is the amount of time the senior class travels, so they are hiking for X hours. And we just finished saying here that because the junior high class started ahead of time, they traveled 1 hour longer than the senior high class traveled. However long that is, X, they traveled 1 hour more. Now, what's their rate? Oh no. See, you've already forgotten. Go back and look in your problem again, and it says junior high class travels 3 miles an hour. Senior high class leaves an hour later, and they travel 5 miles an hour. So we now have a rate and a time for both of these classes. And how do you figure out what the distance is? We're going to calculate it. Now I wrote in miles per hour because that's how fast they're going, but we're not going to show those in our formula. The rate was 3 and 5. So what's the distance going to be equal to? For the senior class, the distance is going to be 5 times x. 5 times x is 5x. For the junior high class, the distance is going to be 3 times the quantity x plus 1. Because we have rate times time. Okay? Now we have all of the pieces of information filled in our chart, and we should be able to come up with an equation. Well, what in the world are we going to do? To have an equation, we have to come up with 2 quantities that are equal. So we say this is equal to this. Well, I'm looking here and I see something that's the same. We have it written here in our sketch, but it's hiding now. The distance that both classes hiked is what is equal. It took them different times to get there because they left not at the same time. They were traveling at different rates, but the distance that they covered was the same. That's like if you're starting with someone, if you're racing with someone who is not as fast as you, you give them a head start. So they might start 20 feet ahead of you. They might start a quarter of a mile ahead of you. I said you give them a head start of 20 feet. I don't, on races that go around the track, maybe that's the way it is. But what I meant to say is, I say, okay, I'm going to stand here at the starting line, and you get a 15-second head start on me. Or you get a 3-minute head start on me. Or if you're doing a Boston Marathon, maybe you get an hour head start on the leaders. But the distance that you travel is still the same. So the equation that we're going to set up is that the distance that the junior high class travels, 3 times the quantity x plus 1, is going to be the same as the distance that the senior high class travels. Now take a look at that and make sure that that makes sense to you. They both travel the same distance. We plugged in our pieces of information over here. The junior high class traveled 3 miles an hour, and they traveled for 1 hour longer than the senior high class. Senior high class, we based our unknown variable on the length of time that they traveled, and they traveled at 5 miles an hour, so their distance is 5 times x. Now you have a very simple, very straightforward problem to solve. First you have to distribute. You have 3x plus 3 is equal to 5x. Now we want to isolate the variable on one side of the equation. I'm going to choose to subtract 3x from both sides of the equation because then I end up with a positive variable. Minus 3x plus 3 is equal to 5x minus 3x. We complete that problem and we have 3 is equal to 2x. Divide both sides of this equation by 2 and we end up with the solution x is equal to 3/2. And at this point you're going to stop and think, does this make sense? Okay, exactly what is it that I'm looking for, and why did I end up with a fraction. So what are we looking for? We're looking for the time the senior class hikes. 3/2 right here. Now I don't know about you, but if I'm talking about the time that it takes me to get somewhere and I'm going to drive an hour and a half, I'm either going to say 90 minutes, took me 90 minutes to get there, or I'm going to say it took me an hour and a half to get there. I am never going to tell you that it took me 3/2 of an hour to get there. So this is an example when you really do want to take your reduced improper fraction and convert that into a mixed number, because that's more meaningful to the problem. So 1.5 hours is the time the senior high class traveled, the time the senior high class traveled. So make sure that your answer is reasonable. Make sure that you've answered the questions. Make sure you've labeled it properly. So, if the senior high class traveled an hour and a half at 5 miles an hour, that says that they traveled a total of how far? They traveled 7.5 miles, I believe. Let's see what happens. Now, the junior high class traveled an hour longer at 3 miles an hour. So they traveled, now even though they didn't ask us this, they traveled 2.5 hours for the junior high class. If they travel 3 miles an hour for 2 hours, they go 6 hours. Another half an hour, they go another 1.5 miles. So you have 7.5 miles again for both the junior high and the senior high class. And that's a way that you can go back. First you can see, yeah, this looks pretty reasonable, that they'd go for a walk, an hour and a half. And when I compare the actual distances, when I plug in the values that we have for the variable, then we have demonstrated that we've solved our problem correctly. So what are you going to do with motion problems? You're going to take the time to look at them, to read them carefully, make sure you understand what you're looking for. You're going to come up with a chart where you fill in all the pieces of missing information, and the rate times the time is equal to distance. And then you're going to look at your word problem and you can say, okay, what exactly is it that is the same? What two things are equal that I can compare? So that's the end of the first part of this video. I am going to go ahead and do the second part just where I do one more problem so that this video does not stretch on forever.